Welcome to our program, Astronomy for Everyone. As you can see, we're not in our usual studio setting. Instead, we're here in Garden City, Michigan at Webster Telescopes, a manufacturer and designer of truss mount style Dobsonian telescopes. With me is Eric Webster. Eric, welcome to the show.
Thank you.
We're going to talk with Eric today about the types of instruments that he builds. We'll spend some time talking about the individual scopes, and then we'll take a look inside at some of the construction processes that he uses. Eric, what about this scope behind us here?
This is a 22-inch f3.6 telescope. It's our second most popular model, just behind the 28-inch. It's small enough for anybody to set up, and the full setup time from rolling this out of the back of your pickup to actually assembling is about 5 minutes.
Oh, that's pretty quick. There's not much, obviously, to setting it up.
Now, we've got 8 clamps at the bottom and 4 clamps at the top, and that is it. You don't need any tools, you don't need any nuts, you're not fumbling with things in the dark. It just literally drops together only one way.
Now, what's the range of telescopes that you make size-wise?
We make them from 14.5 inch and generally up to 40 inches, although we did do a 55 inch a year or so ago, and that was our largest one we've ever built.
And they're all of the truss mount Dob style?
Yes, all truss style.
Why big Dobs?
Yeah, because aperture is king. You know, it's you could have the longest telescope, you could have this or that, but nothing is going to beat having the largest optic there to see the most resolution and the brightest image.
So we're gathering the most photons.
Exactly.
Well, you mentioned optics. Can you tell us a bit about the mirrors that you use for your telescopes?
The mirrors we use are Zambuto mirrors up until 20 inches, 20-inch all the way to 36-inch Kennedy optics, and then anything larger than that is Lockwood optics.
And these mirrors you purchase from these manufacturers to the specification for the scope that you're building?
Sure, someone will want a custom scope. Like somebody will say, you know, instead of a 3.6, I want an f3 so that the eyepiece is way down here for my kids, or you know, a shorter person may want a shorter telescope. Or maybe they're handicapped and a ladder just wouldn't work for those last couple steps they would need on a taller scope. So an f3 or all the way down, we did a 30-inch f2.5 that went out to mainland China. So again, it can be custom made for anybody.
And of course, these seem to be quite easy to use, very intuitive. If you could show our viewers quickly how easy they are to maneuver.
Yeah, even though this is a rather large scope, you can move it just with 2 fingers. You know, the whole thing just moves like butter.
Very smooth and effortless. They come in a variety of finishes. I see this one happens to be sort of a violet color.
Yeah, this is going to an employee or possibly an owner of the Hoosier Tire Company, but we've done them in blue and hot red, and we got a new malachite green color that is a deep, deep green that it looks great.
I know you showed that to me in the shop just a little earlier, and that is a very sharp looking finish. Now, you make telescopes for people. What about someone who'd like to build his or her own telescope? Do you help with those folks?
Yeah, we do. We build scopes as kits, so we could build you all the parts, and you could glue it, stain it, sand it yourself. We also sell all just the individual parts, so if you wanted just the clamps, you know, something that'd be very difficult for the average person to manufacture, or our mirror cells, which we'll take a look at later. You know, we have a CNC machine. It can make 1 or 1,000, and they'll all come out exactly the same. So yeah, if somebody was going to build their own and maybe had a certain skill set and said, hey, I could do woodworking, but I can't weld, or I'm a great welder, but I couldn't possibly finish a piece of wood. Whatever you need, we're glad to help out on the parts we can.
All right, good. It was very interesting to know. Now, I noticed, too, that you offer special services, and wondering if you could elaborate to our viewers what those are.
You know, a lot of times people have an older telescope and it will have an old style mirror cell where, you know, just the pieces just rock along on a rusty bolt, or, you know, someone will want to update their scope with newer optics, which will bring the eyepiece height down. Or maybe they have old wooden clamps and they want to go with the, you know, high-tech aluminum ones or something like that. We can take, you know, the basis of somebody else's scope and tighten it up and make something easier to assemble that doesn't need any tools, or put full go-to on it where you just, you know, point Saturn on the computer and the whole scope just whizzes off to Saturn and tracks it all night.
So you do offer a go-to capability with these types of scopes?
Yes, we do. We have go-to for all of our scopes.
Very interesting, very interesting. Now, I was reading on your website recently that you have a new process that you're working on, and so I get it right, I'll read it. The Active Counterweight and Damping System. What can you tell us about that?
It's a computerized system, and what it does is that if it's kind of breezy today, but if it was windy, the scope would kind of act like a sail, and it would vibrate in the wind. The active damping system reads that wave. Let's say it's a 12 hertz wave. It will issue the anti-wave and cancel it. So, if we knock on the scope and make it vibrate, it'll actually cancel that vibration, giving you a much clearer image.
Okay, we talk about vibration and damping down on telescopes, especially if you're slewing, if you have the go-to with the motors, and that little wiggle or jimmy that is present, or on a slightly windy day, that can be a real problem at higher power eyepieces. Just watching that image just in the eyepiece, very annoying. I can speak from personal experience about that. Your production facility that you have here, how long have you been doing this?
Almost 20 years.
20 years. The woodworking and the telescope making?
Yeah, initially we were just a woodworking shop, and we were building, cabinets that could hold an 8,000-pound aquarium. Very stiff, very large thing, and that translated nicely over to telescope building, because telescopes have to be very stiff. Any bit of flexure and the mirror will go out of collimation. So, we need it lightweight, but we need it as stiff as it can possibly be made.
And what propelled you into making telescopes away from what you had previously done?
My grandfather always had a 10-inch scope that was a yard cannon. People thought it was so huge as 10 inches. And of course that gets into your genes, and as you grow up around that kind of thing, you only want to build something bigger and better. And nowadays, here, this is 2013 when we're doing this interview, a 10-inch scope is considered kind of a small scope, or possibly someone's beginner scope. But back, 20, 30 years ago, that was a big telescope.
Yes, it was, and telescopes have come a long way in all the intervening years. We hope you found this to be quite interesting. We're going to step away for just a second, and we'll take a break to bring you Term of the Month. And right after that, we'll be back going inside the shop to go over some of the actual techniques that Webster Telescopes uses to make these amazing instruments. Don't go away. We'll be right back.
The term of the month for July 2013 is binoculars. I'm going to be talking about 4 types of binoculars, and the first type is the most common type, the poroprism binoculars. These are the type of binoculars that you have sitting at the back of your closet, underneath your shoes and stuff, that's collecting dust. But they're really good for astronomy and for bird watching. They have good light, they have good magnification, they're relatively inexpensive. The prism in a poroprism binocular, shown on the right side of the image, is a relatively simple prism, and its purpose is to take an upside down and backwards image and make it right side up and non-reversed. So it's the image that you see normally with your eyes, only brighter and magnified. There is another type of prism which is a little more complicated, and so the light bounces around a little bit more in this prism system, and they're used for roof prism binoculars. Roof prism binoculars, which is the next image, they're more compact, and they tend to be a smaller diameter objective lens than you get with a poroprism. But they're very compact, they fit in your pocket, they're very light, you can hand hold them for quite a while. And they're also not that expensive, but they're not as bright an image as the poroprisms, and but they are very much smaller. There's a reverse poroprism binocular which has the same sort of poroprism as your normal 7x35s, but they're usually for smaller objective lenses, and the two objective lenses are actually closer together rather than farther apart. Finally, we have the Galilean binoculars. These are very uncommon. They're typically used for opera glasses, and they often combine a relatively large objective lens. I've seen some that as large as 40 millimeters, along with low power, and I've seen them maybe in 2.5 power, as opposed to 7 power or 10 power for other kinds of binoculars. And these binoculars have great wide fields of view and decent light gathering, but they have some problems if you have astigmatism or other eye problems. They're not necessarily the best for that, but they're great for wide fields of view. And that's the term of the month for July 2013, binoculars.
Eric, I was wondering, could you point out the various components of this telescope?
Yeah, sure. Here we have the finder. What this does is it superimposes a bullseye target up onto the sky, and that way you can just look clear through it. There's no magnification, so it's a very natural way to find your way around the sky. Then we have the focuser. We only use feather touch focusers. There are no finer focuser made. We had a machinist a couple years ago who worked in our shop, and he says, "Oh, I'll make you a bunch of those." And I said, "Great." And I handed him one, and he played with it a little bit. He's like, "Oh, wow. Well, I don't know how many of these I could make. What do you pay for these?" You know, like he just suddenly got a reality check when he felt just how many ball bearings run that whole system. Then we have our clamps. These clamps hold the 2 trusses. And this way you only have 4 pairs to carry around rather than 8 individual trusses to wrestle with like an octopus. Then we go down. These are anodized aluminum trusses. They're hollow and lightweight. And we have our truss clamps here at the bottom. And then we have cast aluminum side bearings. These will never warp or bend or anything like that, so they'll stay accurate the entire life of the scope. Then the mirror box right here, it holds the mirror. It's kind of the central brain to the entire telescope. And then finally, we have the rocker box here on the bottom. The rocker box allows the scope to rotate in every direction in alt and as, and we cover it with a Rodex material. This stuff cannot be burnt, kicked, acid-proof, tear-proof. They use it on boxes for touring bands and things like that, and if it can handle a bunch of 300-pound roadies throwing them around the whole country, then certainly it's going to handle the telescope really well.
Thanks, Eric. Welcome back. We're here inside the shops of Webster Telescopes to take a look at some of the manufacturing techniques that they use to make these marvelous telescopes. Eric, what's the first piece we want to show our viewers?
Well, probably the most critical part of any telescope is the mirror cell. The mirror, if it was the size of Las Vegas, the tiniest imperfection would be a human hair laying on the Vegas Strip. It is that precise. There is nothing machined anywhere that is a finer machined surface than a telescope mirror, properly made, of course. You know, when someone will say, "Oh, at work we work in 100,000, you know, or this or that," here we're working at 1/4 of a wave of light. It cannot be compared by anything you could measure on a micrometer or something like that. So we need support that can hold that mirror. Thermal from just your hand touching it. If you have a mirror on a test stand, we'll put a huge hump, you know, into the actual surface where the Pyrex expands from just the heat of your hand. So it's really critical. So here we CNC the cell, this is what it's called, and it holds the mirror. And every part of the cell is a spherical bearing like an eyeball. So, you know, this part rocks like that, and then this part here rocks, and then this can be adjusted underneath. So this looks like a crazy contraption. It looks all sloppy, but when we put an actual mirror on it, and here is our dummy wooden mirror, you notice that the whole thing is rock solid. It cannot wobble. Everything is triangulated down, and like that old saying, a 3-legged stool never wobbles, this does not wobble. We've had customers where this has fallen out of the back of their pickup trucks where they didn't latch their door on the back of the gate, And the mirror was undamaged, even though the scope took a little bit of damage from falling out. So these 3 pins would be lowered, and then they would hold the mirror actually in place.
Very interesting, very interesting. It's always wondered how these types of mirrors are supported, especially at these larger sizes.
Yeah, the bigger it is, the more flexible it is. You know, if you make something twice as large, it's not twice as flexible, it's 8 times as flexible. You know, you have that cubic law that ruins it for everybody. So yeah, a mirror just a little bigger has a whole lot more flex that has to be supported.
What's the next piece here to demonstrate how a telescope is made?
This is a cutout piece. We use all dovetail construction, and I don't know if anybody out there in viewerland has ever bought drawers, you know, for their kitchen cabinet or something, but you know, it's about 4 times the money for the dovetails, because even without glue, you can't pull them apart. It is just the strongest construction there is. So everything is assembled, dovetailed, and then it's braced from the inside in 2 ways. So this cannot be flexed or shattered or whatever. Like I said, this has fallen out of the back of people's pickup trucks and it has not been damaged. It is not broken apart.
Obviously, anything that would flex would be very detrimental to your optical path of your telescope.
Exactly. We need light and we need stiff.
Well, what type of materials do you use to make these boxes? Do you just go to Home Depot and buy some plywood?
That's funny you ask. Here's a piece of Home Depot plywood. You see there, I don't know if we can hold this up to the light or not, but you can see there's a lot of voids in it. It's made of 5 plies. It'll say it's oak, but it's pine all in the middle. There's just a paper-thin veneer of oak on both sides. Here is a piece of the wood that we use, and this wood comes from Russia, and it has 15 plies. Every ply is made of birch, and it is glued together with exterior glue. I have a sample of this that has been floating in a jar for like 13 years, and it has not delaminated, it has not come apart. I mean, it looks just like this does, but it's been floating in a jar of water.
So this material is very structurally stable. There's no twist or warp or wave to it like you'd see on a sheet of OSB at the local lumberyard.
Yeah, no, it comes in 5 by 12 sheets, and you can just sight it like a gun, and it's just completely straight. It is the superior wood. You know, it's lightweight, but it doesn't flex, it doesn't warp, and it doesn't delaminate.
Very interesting. What's this next piece we have here?
Well, earlier we were talking about how we kind of cater to the do-it-yourselfers, and one of the most popular things that we send all over the world every week are the clamps. So people will buy a set of the clamps. This would go on your mirror box right there. And then you have your aluminum lightweight trussing. And then, like I said before, here we combine each truss into just a single unit. So you only have 4 pairs rather than always wrestling with 8, grouping them together. So this could be used on a scope, you know, maybe this f1 14-inch here, or it could be used on a 30-inch scope. And for really large stuff, like the 40 and up, we even have 2-inch size truss clamp sets that we send out, and that way you can use it on the true beasts of the night.
All right, well, I wanted to check too. Behind us we have the upper part of the telescope. Is that made with this same multi-ply birch plywood?
Yeah, it is. You know, this entire, we call this the upper tube assembly, and it would have a skin on the inside to block the light. But as you see, this entire thing, even though this is for a 24-inch telescope, this only weighs 6 pounds. You know, it's very lightweight.
Indeed, indeed, and yet it has the strength.
Exactly. We're not going to be able to flex this or bend this or warp this. This will hold. The focuser would go right here. The finder would go right there, and all it would need to be finished would just be a center light shield to keep the light, stray light, from coming into the focuser.
Interesting. As far as the size of the mirrors, I know we talked about that a little bit earlier, but we've got some templates here that I think we can use to demonstrate to our viewers about that.
Yeah, we should show them that. Here, for instance, would be a 32-inch mirror, and this would be a 14.5-inch mirror. So you can see that 14-inch mirror, you'd need 4 of those to even come close to the light gather you'd have on a 32. And if you think this 32 is big, you should see when we're wrestling a 40 off the chain lift and lowering it down to the scope for the first time. It'll raise a few hairs on the back of your neck.
I would imagine it makes for some tense times until it's settled down safely into place.
Yes, exactly.
what does it take as far as time-wise to build one of these telescopes?
Most of the time taken is waiting for the optics. You know, a large optic like the 32 that we just looked at, that might easily take 6 to 8 months to fabricate. A smaller one like that 14, it might take maybe 4 months to have done. So normally we have the scope completed by the time the customer's mirror has come in.
I see. So you've got these things happening consecutively, building the scope itself and having the mirror fabricated, and then bring the whole thing together.
Exactly. The optician's working in their shop, and we are crafting in our shop. And then finally, when it's sent to us, we take it outside and we really use it. You know, we don't just put it all in a box and say, yeah, here's your telescope. We literally have taken the scope outside under starlight, and we test the go-to, we test the optics. That way when the customer gets it, it's a completely tested 100% working system.
So your customer has complete confidence in the scope that he takes out, that it's ready to go.
Yes, yeah, exactly. Some people will come to pick it up, but about half of our customers are overseas. So I imagine in the next few years, maybe 60% or more of all our product will be heading out overseas.
Well, that's kind of good. It's good to know that we can send out some product that says proudly made in the USA.
And that's us, Webster Telescope, proudly made in the USA.
Well, we hope you've enjoyed our visit here at Webster Telescopes today to gain an insight, pardon the pun, on how a telescope is made. If you'd like more information, you can visit their website at webstertelescopes.com. Hopefully we'll also have that down at the bottom of your screen as well. And don't go away, because right after this, we'll have What's Up, so stay tuned.
What's up for July 2013? The month starts in the third quarter moon. Really, it's day 0. It was the last day of June was the third quarter. So the month sort of starts out, if you will, on the 8th. We have the new moon. This is a Monday, and all of the phases in July are on Mondays. So the first quarter, which is up in the evening, that's on the 15th, Monday the 15th. And the full moon is on the 22nd of July. The third quarter, which is visible from about midnight and into the morning, and really almost till noon, the third quarter is on the 29th of July. So we end the month sort of in the third quarter also. In mid-June, all the way to mid-July, there is a meteor shower called the Eta Aquarids, and it peaks, it has kind of a fuzzy peak, it peaks somewhere between the 4th and the 5th of July. So, you know, there's a third quarter moon, there's a little bit of, the third quarter moon rises after midnight, so if you stay up too late, then the moon will wash out some of the meteors. But it's a good show this year. And to watch the meteor shower, or any meteor shower, you might think, oh, well, it's hot, it's been July, it was hot all day. It might be very cold at night, and when you're watching meteors, you're really not moving very much. So bring a blanket, bring a hoodie, bring something warm to wear. You won't need binoculars or a telescope. Just lie down, look up, try to catch as much of the sky as you can. Now they're called the Eta Aquarids because if you trace back meteors, they will appear to have originated in the constellation Aquarius. But that isn't important for actually enjoying the meteors. What's important is seeing as much of the sky as you can so that you catch them. They zip by, zip, and if you say, oh, there's a meteor, it's too late. It's already gone. So you can say, well, I saw that one, but don't try to point them out. That's just not going to work. They're really quick. Venus is visible in the west just after sunset. It's maybe 4/5 above the horizon, so it's just a little less than 20 degrees, maybe 18 degrees above the horizon in the middle of the month. So Venus is pretty bright, so you can usually spot it without binoculars. Binoculars can help. Wait until the sun has set, because looking at the sun, even without binoculars, is painful. Looking at the sun with binoculars without a solar filter is blinding. Please don't do that. Saturn is in the constellation Virgo, and on the 15th of the month, it is accompanied by a first quarter moon. So that makes it just easier to spot. The rest of the month, you might see at the very top of the screen, you'll see the star Arcturus. And Arcturus is easy to find. You find the Big Dipper, and you follow the handle, and you arc down the handle to Arcturus. So you arc to Arcturus from the north, and it's a bright star. There aren't any other bright stars right there. And pretty much below it, you can kind of see Saturn and the constellation Virgo. And Saturn's rings are tilted over, and they're really gorgeous in a telescope. Neptune is in Aquarius also, or right, Neptune is in Aquarius, where the Eta Aquarii meteors seem to come from. You'll need a really good finder chart to find Neptune. You won't be able to see it naked eye. In a telescope, it is this sort of greenish blue color. Uranus is just to the left of Aquarius in Pisces, and although in a very dark sky you can see Uranus naked eye, you really need a telescope and a really good finder chart to find Uranus. In fact, Pisces itself isn't that easy to find. Pegasus, the great square of Pegasus, is above Pisces. So Pluto is very difficult. It's a very difficult object to spot. It's 14th magnitude. You'll need a pretty big telescope. I've seen it in my 10-inch telescope. I don't think you can go much smaller than that. Pluto is in Sagittarius, but it's near M25. This is an open cluster in Sagittarius. It's only 2 degrees from M25. So M25 is a good object to see by itself. So get a really good finder chart to look for Pluto. And that's it for What's Up in the Night Sky for July 2013. Look up in the sky. It's the greatest show. Just look up, and it's absolutely free.